morning to everyone. We from Savita Engineering College, greetings to all, and I welcome all the participants for the webinar. And let me introduce our guest for the day, Dr. Manoj Mohapatra, and he's a senior scientist in spectroscopy section of Radiochemistry Division, Bhabha, Trombay. He joined the organization after completing the 46th batch of Bhabha Training School Scheme 2002 to 2003 in chemistry discipline. He did his doctorate from Homi Bhabha National Institute, Mumbai, and was on deputation to CEA, the Atomic Energy Commission of France, in 2013, and to ICTP, the International Center for Theoretical Physics, Italy, in 2016. His research interests mainly include understanding the structural property of correlation of lanthanide and acetonide doped compounds, radiation-induced charges, radiation-induced changes in materials, and chemical quality control of nuclear materials. He is the recipient of DAE Young Scientist Award in 2014, DAE Group Achievement Award in 2012, and the Outstanding Radiochemist Award in 2010. He has more than 85 journal publications in peer-reviewed journals with citation ranging to 1,881 with H index of 21 and I-10 index of 44. He has many international peer-reviewed international journals and 3 book chapters to his credit. And now I welcome Dr. Manoj for his presentation. Thank you, sir. So, over to you, sir.
Yeah. Can you hear me?
Yes, sir.
Yeah. Good morning to all. So, let me first thank Priya Madam for inviting me to present this webinar, and I'm very grateful to her. And can I have the first slide, please?
Yes, sir.
Yeah.
Yes. Yes, sir. So,
Yeah.
Shared, sir.
Yeah. So I can see that. So the topic, as it was displayed, that it's on the use of lanthanide ions as photoluminescence structural probes. And I have prepared this webinar keeping in mind that most of the audience will be students, research scholars. So in that way, I have prepared it. So please excuse me if the presentation looks to you very elementary. It's only that it's my mistake, and I try to keep it as simple as possible. Okay, so my screen has gone blank. Madam, can you please put on the screen? Yes. So next slide, please. Yeah. So before I start my presentation, I must acknowledge my seniors who have introduced me to this wonderful subject of luminescence spectroscopy, namely Dr. S.D. Godbole and Dr. V. Natarajan, who are former spectroscopy section heads, and Dr. R.M. Kadam, who is the present section head. Also, I am highly my sincere acknowledgements to Dr. P.K. Pujari, who is head Radiochemistry Division and director RC&I group of DRC. Also, my acknowledgements to my young colleagues, Dr. Santosh Kumar Gupta, who is a former Fulbright fellow at USA, and Dr. Nimai Pathak, who are very bright and young colleagues of mine, and I'll be citing some of their works also. So, can we have the next slide, please? Yeah. So let me start from the basics. What is photoluminescence? As the name suggests, that luminescence is basically emission or observation of light or photons, and similar to luminescence, it's a collectively we call it luminescence, and similar to photoluminescence, we have thermoluminescence when the excitation is by thermal energy and the output is in the form of light or photons. In case of photoluminescence, there are two types of photoluminescence phenomena. As we all know, one is fluorescence and one is phosphorescence. And similarly, there is something called as chemiluminescence, where we are getting light emission by excitation by a chemical reaction, chemical phenomena. Bioluminescence, where luminescence is observed in biological species like fireflies and several deep sea creatures, which show vivid colors. In fact, bioluminescence is a form of chemiluminescence also. There is triboluminescence also, where is excitation is by mechanical force such as pulling, crushing, etc. So these all types of things are called as luminescence. Now basically what we are going to deal with is that photoluminescence, where the excitation is by a light or a photon and emission is also photon. Next slide please. So why do you study photoluminescence? What is the advantages? Now see, it's a non-invasive. When I say non-invasive, it doesn't interfere in the system. It's a characterization system which is non-invasive in nature, and it will not interfere in the dynamics, in the rate things. Suppose you want to determine some rate constants. So photoluminescence is one of the best techniques. Now, when we excite, as we know, at the normal state, all the electrons are in the ground state. When we put a photon energy, it absorbs the exciting light and goes to the excited state. Now, once it goes to the excited state, it has two ways to come down. Okay. Now, one is that from the higher excited states, can I have a cursor, please? Yeah. Yeah. So when the excited state, it comes back to the ground state, it has two ways. One is the phosphorescence and one is the fluorescence. As I told you that these two are combinedly called as fluorescence. Now, apart from that, the advantages of photoluminescence is that it provides triple resolution. Triple resolution in the sense, suppose there are two types of species, but the number of coordination is different. Let us say I have an iron complex, okay, iron 3+ complex. Now, but one is iron aquo complex and one is iron bound to, let us say, some other metal, some other ligand, let's say ammonia. Now, in normal conventional conventional, let us say, UV visible absorption techniques, it's not possible to distinguish. But here you can distinguish not only the oxidation states, but the coordination geometry and the ligand ion also you can distinguish. Now, apart from excitation and emission, there is something called as lifetime of fluorescence levels or photoluminescence levels. That is the time taken for the excited state population to become 1 by E, or roughly, if we take E is equal to 2.7 or 8, then 1/3 of the original value. Suppose the time taken for 100 number of electrons in the excited state to become 1/3, that is 33, that is the lifetime of a particular species, and it is characteristic of a species, not only of the oxidation states, it also characteristic of the coordination geometry. Suppose the coordination geometry changes, the lifetime will also change. So by fluorescence, we get temporal resolution also, like excitation, emission, and temporal resolution. And thus, we can achieve signal to noise ratio better. Also, in case of photoluminescence, you can use a suitable laser to excite. Since in photoluminescence, we are actually detecting at 90 degrees, the emitted light is detected in 90 degrees. So you can increase the excitation photons, number of photons which is being excited, so that the signal automatically increases. Okay, so that is the one of the main advantages, that you can get triple resolution and higher signal to noise. Also, it is non-invasive and non-destructive in nature, so your equilibrium is maintained. Okay, can we have the next slide, please? Yeah. So since we are going to do, we are going to have a discussion on lanthanides, I thought I would better say lanthanides vis-a-vis rare earths. Now, people use lanthanides and rare earths interchangeably, but they are actually different. So as we see, this is the periodic table. I have highlighted the lanthanide part, cerium to lutetium, but if you include yttrium and scandium, then it's called as rare earths. So all the lanthanides, that means 4F series plus yttrium and scandium, are called as rare earths. Now, why they are called rare earths? They are not so rare. They are, in fact, cerium is the 25th most abundant element on the Earth's crust, but they are very rare to separate, actually, to isolate. It's their isolation is very difficult. That's why they are called as rare earths. Okay, can we have the next slide, please? Yeah. So these are all the rare earth ions. I have, if you look closely, I have mentioned the oxidation states. If you see, most of them are stable in the 3+ oxidation state, like most of them. So by losing the S and D electrons, the F electrons are there, and that is the most stable oxidation state. That is why by losing one S electron and two D electrons, two S electrons and one D electron in some cases, they are the most stable oxidation state. Okay, next one, please. Yeah. So if we compare lanthanide ions versus transition metal ions, like actually this is actually asked in many interviews. If you for research scholars or students, if you go to an interview, maybe some absorption interview or something like that, yeah, you are asked, this is a very common question, what is the difference in between lanthanides and transition metal ions vis-a-vis the spectroscopic techniques? Now the common answer is, now in transition metal ions, what is happening is that it's the 3D elements or 4D elements. Those orbitals are outside. That means the ligands can directly influence the transition metal ions so that their spectra are broad. But in case of lanthanides, they are 4F orbitals and they are buried deep inside the nucleus. It's inside the atom. So they are not exposed. That is why one may expect that the transition elements will show a broad band. I will come to that. Why broad band? Why sharp band? And lanthanides will show a sharp band. Also, the ligand field actually cannot influence the lanthanides because they are shielded. In case of transition metals, they are not shielded, so the ligand field, electrons of the ligand, can influence the electronic field of the metal ions. So basically what we are dealing here is that in case of lanthanides, we can experience FF and FD transitions, and each lanthanide ion has its own characteristic emission. So from the emission, by looking at the emission, you can identify which lanthanide ion it is, just by looking at the emission. And they are also characterized by narrow emission bands. Now, why narrow, why broad? I'll come to that. Also, lanthanide ions are characterized by long excited state lifetimes. Now, why also long excited state lifetime? That also I'll discuss in the next slide. Next slide, please. Yeah. Suppose if you compare lanthanides versus actinides, what happens is that, as I told, that lanthanides, when electrons are excited from the ground state, it goes to the excited state, and by successive internal conversion, they come to the lowest possible state, and from there they give emission, which is in the visible region. That is why you will see most lanthanides are colored. But in case of actinides, it's a 5F system. And 5F system, there are number of energy levels are much more, and that is why the energy levels are provided like a ladder-like pathway. So once the electrons are excited to the excited state, it provides a ladder-like pathway for the energy to dissipate in a non-radiative manner. When I say non-radiative, that means the output is not in the form of light or photons. It's in the form of heat energy or phonons or vibrations. So that is why if you see, most of the lanthanides are colored. They will give emission, colored emission. But in case of actinides, they will not give colors. That is why most of the actinides are non-colored species. Of course, the exceptions are americium 3+, curium 3 plus and uranium, but uranium, it's a charge transfer band, not an FF transition. So most of the actinides, FF transitions are non-photoluminescent, and in case of lanthanides, they are photoluminescence active. Next, please. Yeah, that's what I was talking about, that broadness. Now this broadness comes from fast and slow. As we know, if a transition is allowed, it's fast, okay, and if a transition is forbidden, it's slow. Now uncertainty principle tells that delta E into delta T is equal to H cross. So if the transition is fast, we are expecting a shorter lifetime. If the transition is slow, that means if it is a forbidden transition, we are expecting a longer lifetime. Also, as I told you that delta E into delta T is equal to H cross. So if delta T is fast, that means small, then delta E has to be large. That means the spectra will be broad. Okay. Similarly, if it is slow, the transition is slow, that means delta T is very large. Slow means it takes time, right? So delta T is large, so delta E has to be small, it should be narrow. Okay, so similarly, that is how we can see that FD transitions which are allowed, and we know that selection rule states that electronic transition selection rule states that delta L is equal to plus minus 1. So FD transitions, PD transitions are fast, shorter lifetimes and broad. But if we see in case of lanthanides, basically FF transitions, DD transitions are forbidden, slow. That is why they are sharp. Okay, but one may say that one may argue that in case of transition metals, though they are DD transitions, they are broad. That is because in case of transition metal ions, the ligand influences greatly the ground and excited state. That is, the nature of the electron wave function of the ground state and excited state are totally different. Okay, because the ligand is also influencing the electronic field. That is why you will see a broad transition in case of, although it is forbidden, you will see the broad in case of transition metals. But in case of lanthanides, that is not possible because 4f orbitals are buried inside. So the ligand cannot influence it. That is why you will see a sharp transition. Now, if you see the figure, left-hand side figure, red color figure, it's a typical Europium 3 plus spectra, which shows both Europium 2 plus signature and Europium 3 plus signature. Okay. So this part is because of Europium 2 plus, and this part is because of Europium 3 plus. So as you can see, this part, Europium 2 plus, is broad. Why it is broad? Because it is an allowed transition, and Europium 3 plus is a FD transition. So if you see broad transition, it definitely means that it's an allowed transition. Suppose charge transfer transitions like ligand to metal charge transfer or metal to ligand charge transfer, they are broad because they are allowed transitions. Similarly, if you see this transition, this part here is actually sharp, very sharp, because this is forbidden, and this is because of FF transition. So the sharp one is FF because it is Europium 3 plus, and this one is broad because it is allowed transition, FD transition. Next slide, please. Okay. Now there is a correlation in between lifetime and symmetry of a particular ion. This we have to keep in mind because this will be using it further to use lanthanide ions as structural probes. So as I told you that the PL decay time, PL means photoluminescence decay time, or we simply call it lifetime or decay time, is equal to the time taken for the excited state population or the intensity to become 1 by E or 1/3 of the initial value. The value are characteristic and thus serve a fingerprint. So when we are studying a system, we not only look for the emission wavelength, excitation wavelength, also we are looking for the characteristic lifetime of that species. If that species, particular species under investigation, is present in a symmetric environment means the Schonfly symbols or the group it represents, the symmetric group, is very high. Let us say octahedral. It's a very high symmetric environment with I, that is inversion symmetry. The selection rules are strictly followed because D is a pure D. As we know, D is gered and F is ungered. So Gerard to Gerard transitions are forbidden. Gerard to un-Gerard transitions are allowed. So it's a D-D transition that is forbidden. But if it is not present, like symmetry is very low, then I is not there. That is inversion symmetry is not there. Then G, how do you define? How do you define Gerard and un-Gerard? Because it's in the I. I decides if there is a presence of I, then it is Gerard. If there is absence of I, then it's un-Gerard. So if there is no symmetry, then D is not pure D. F is not pure F. So there is, we call it FD mixing or DP mixing, we call it. So if the center of symmetry is not there, then the forbidden transitions, the allowed transitions also and forbidden transitions also are very high. The intensities are very high, okay? Because the selection schools are lifted. So that is why, if by just looking at the spectra, we can say what is likely to be the symmetry of a particular metal ion. Okay, so that is the basis of using lanthanide ions as structural probes. Basically, the idea is to probe the structure. What is the structure? What is the symmetry? Or what are the number of coordinations around the metal ion? So if the metal ion is having a symmetry, higher symmetry, then you will see a different signature. If you are not seeing if you are not seeing that particular signature, the symmetry will be lower. From that we can deduce it. It will be clear when we go to the examples, specific examples. Next, please. Yeah, no, but some people may ask, why studying local structure? Why it is so important to see the local structure or structure? Now, as we know that structure actually plays a very important role in the property, especially in a functional material or even a multifunctional material also. Now is the time when we are looking towards multifunctional materials applications. So the application actually is predominated, is dictated by its structure. So if you don't know the structure, how you can predict the application? So the if we study the dopant ion, suppose we take a matrix and dope a particular metal ion and it distributes in the host. Now it will lead to a better understanding of the correlation between the structure and property. As I told you, the structure dictates the property. So if you desire a particular application, then you need to optimize the structure. So they are interdependent. So we need to identify the structure. In such systems, actually, the spectroscopic information related to the local site symmetry is very, very crucial. Okay, as I told you, the actual site symmetry of the dopant ion, it cannot be really revealed from the crystallographic data, because you are using a very, very small amount. Suppose you are using a dopant ion. XRD will tell you a rough structure. But suppose you put a dopant ion in a multifunctional material, where it is going? Is it going to an interstitial site? Is it going to a lattice position? Is it going to replace A ion or B ion? It's not possible from XRD, because XRD will tell you only from a certain point of let us say 1% or 2%. It will tell you. But let us say you are doping 0.5%. It's not possible. So that is possible only if you do a thorough photoluminescence investigation. That will tell you what is the local structure, where the metal ion you are going, you are putting in the material, where it is going actually. Is it going to an interstitial site? Is it going to a lattice position? Or it is creating defect centers, or it is not creating defect centers? These all informations can be obtained by looking at the local structure. Next, please. Yeah. Now, if you see literature, you will see maximum studies has been done on Europium 3+. Okay. Now, if you, it's a very, very simple, very, very humble lanthanide, I will say, and most of the work, if you see, it has been done on Europium 3+. Now, if you take a look at the Europium 3+ spectra, now let us say I have got this type of spectra. Now, what does it tell? Well, first thing is that when you look at this, it will tell you that it's Europium 3+, because as I told you that Europium 2+ will give you this type of broad band. Now, once you get this type of sharp transitions, you are sure that it's not Europium 3+. First, that's it. Only that it's Europium 3+ in +3 state. No, it reveals much more information. In fact, I often tell in my presentations that each peak here, each peak here will give you some information. Each peak gives you a different information that we can use. Now, first is that you can see the peaks are ranging from 550 to 750. Okay. Now, if all these emissions are from, as we can see, from 5D0 level, 5D0 to 7F0, 5D0 to 7F1, 5D0 to 7F2, 5D0 to 7F3, and 5D0 to 7F4. Okay, this is the right side picture shows the energy level diagram of Europium 3 plus, different energy levels. As I told you that most of the absorptions are from 5D0 to 7F levels. But there is another level which is known as 5D1. So this 5D1 level also gives emission, but not in all cases. That emission usually occurs in the range of let us say 430 to 530. In some cases up to 550 also, but before 550. It's not after 550. It will come before 550. Sometimes at 435, 535, that way. So if you are not seeing the absorptions or emissions from 5D1 and upper levels, it infers that europium concentration is high, very high. So if you are seeing the levels, emission levels from 5D1, then the europium concentration level is low. I must say that this is an empirical thing. It's not a absolute thing. It's just a thumb rule. It's just a thumb rule that mostly that if you are not seeing the emission from 5D1, the europium concentration is very high, and you are not seeing because your concentration quenching is taking place for those levels. Okay. Also it infers that you have annealed the system at higher temperatures. Suppose you use a soft synthesis route, okay, like salt gel, then you are most likely to get the emissions from 5D1 level. So if you are not getting emissions from 5D1 level, that means that you have used a higher temperature method for synthesis. Okay. As I told you that cross relaxation among the ions, also thermal quenching is also the reason for not observing the emissions from 5D1. So just by looking at the spectra, you can say two things. The europium concentration is high and you have used higher annealing temperature. Okay, next please. Okay, coming back to the europium spectra, as I told you that each spectra, each peak in fact gives you some information. What are the informations? Now, first thing is that at 580, you can see the first line, this one. This is 5D0 to 7F0 transition. Okay. Now, this 5D0 to 7F transition, F0 transition is known as totally forbidden transition. Totally forbidden. Why? Because delta J is equal to 0. There is no change in the J value. So it's a totally forbidden transition. So you are seeing this. That is, the symmetry is very low. That is why you are seeing this. You should not see this transition in a symmetric environment. Suppose you put a dopant ion, put europium 3 plus in a cubic field or octahedral field, which is very symmetric, then you will not see this transition. The fact that you are seeing this transition, it indicates that the site symmetry of the metal ion is very low. In fact, it is CNV or lower. CNV means C2V, C3V, C4V, like that. Okay, I assume that the audience is familiar with Schonfly symbols. Also, the position of the line and the FWHM of this line also indicates the site distribution. In fact, there is a report which says that if you see, I have blown up this figure 5D0 to 7F0 here. This one. Okay, so yeah, so if you see the FWHM, when I say FWHM, FWHM is full width at half maximum. So this is my half, this is suppose this is my full width, this is half width, so this is FWHM. So if I have to take it to a origin file, then I can see this is FWHM. Okay, so this FWHM, if it is more than 120 centimeter inverse, if it is more than 120 centimeter inverse, then it says that a large site distribution. What do you mean by site distribution? Site distribution means Europium is present at a different sites. It's not a particular symmetry. It's not a particular symmetry. Let us say all Europium 3 plus are in cubic. Then I will say it's a very small site distribution. Suppose I will say that one Europium, let us say some part of the Europium are in cubic, some part of Europium are in tetragonal, some part of Europium 3 plus are in octahedral, and some part all in the same matrix. Huh? So that will say that it's a long side distribution. Let us say glasses. Suppose you take glasses and you record Europium 3 plus, you are bound to get more FWHM in this case. You will be getting very high FWHM. So that indicates that also. So without going to the, suppose I have a glassy matrix, I don't have a XRD, I don't have anything, I have only photoluminescence technique. I can say that it's a glassy phase by looking at the Europium spectra. That's also a very nice thing actually. That's also a tricky thing. That's also a tricky thing to ask in interviews. That how, suppose you don't have XRD, I want to know it's a glassy phase or not, it's a glassy thing or not. What do I do? So the answer should be I put a Europium ion or a probe and then monitor its luminescence spectra. I will see the site distribution. If the site distribution is very large, then I can say that it's a. See again, this is a thumb rule actually. It's not a particular thing. XRD is the ultimate thing, but this is a thumb rule actually. This can be done. Okay, so what are the next things? Also, as I told you, that this peak also gives another information. What is the information? Now, there is something called as Stark effect or number of Stark components. What is Stark effect? Stark effect is the splitting of these these absorption spectra. Now, if you see, there are very small peaks here actually. It's not a single peak. You see, this is not a single peak. There are 3 peaks actually. Similarly, if you see here, there are 2 peaks actually. One is here, one is here. So this splitting of it is called as Stark effect, Stark splitting. So the number of Stark components gives us an idea. The number of Stark components gives us an idea about the symmetry also. So the maximum number of Stark components can be found for a particular transition is 2j plus 1. So if it is a 0-0 transition, that means j is equal to 0. So one component only, because 2j plus 1, I told you, maximum number of Stark components one can observe is 2j plus 1. That is 1 for this line. This is 1. So if you observe a splitting here, that means it's not a single Europium ion. There are multiple Europium species. Like one Europium may be in a different coordination environment. Like one Europium is coordinated by 6 water, or another Europium is coordinated by 5 water and another ligand. So that means 2 different types of metal ions. So from observing this number of splitting, you can identify how many types of Europium ions are present without going to the lifetime values. Like I told you, lifetime is an indication of number of species. So suppose you don't have lifetime spectrometer. Suppose you don't have a fluorescence lifetime spectrometer. You have simply a fluorescence spectrometer, not lifetime. From that also you can identify, you can have a guess that how many types of species are there. Suppose you get only 1 peak here, that means 1 type of Europium. If you get 2 peaks here, then there are 2 types of Europiums are there. Okay. So thus star components, number of star components, it gives you a very good idea, very precise idea regarding the site symmetry. Okay, next please. Yeah, next comes the asymmetric ratio. See, as it is known that there are multiple transitions, as I told you, 5D0 to 7F1, 7F2. Now, if the delta J is equal to plus minus 2 or plus minus 4, those transitions are called as electric dipole transitions. And if the delta J is equal to 0 or plus minus 1, those are called as magnetic dipole transitions. Okay, except, as I told you, except J is equal to 0 to 0, 0 to 0, that is totally forbidden. Now, selection rules, as I told you, selection rules for ED transitions tells that delta L is equal to plus minus 1, and for magnetic dipole transition, delta L is equal to plus minus 1 and 0. The asymmetric factor, or A, is represented by the ratio of the one peak, that is 5D0 to 7F1 peak, and 5D0 to 7F2 peak. This is the 2 peak. This is the 1 peak. So the ratio of these 2 peaks is called as asymmetric ratio, because one of the transitions, that is 7F1, is a magnetic dipole transition whose intensity doesn't change. If you vary from host to host, the intensity of this magnetic dipole transition doesn't change, but the intensity of this fellow here, 5D0 to 7F2, it changes depending upon the symmetry. So the ratio of these two gentlemen tells us the asymmetry or symmetry of the particular species of the metal ion in that environment. So if you have a very symmetric thing, then this fellow is not allowed actually. This is always allowed. So the intensity pattern is different. Now, in this case, if somebody looks at this emission spectra, one can say that clearly that this is an asymmetric environment, because I can see 7F2 is highly intense than 7F1. Its intense means it should be small, because it's a electric dipole transition, and electric dipole transitions are not allowed. Okay, electric dipole transitions are not allowed, so it should be small. So it's highly intense means the symmetry is very low. So just by looking at it, I can say that the symmetry is very low. Similarly, this is not only valid for Europium 3+. This is also valid for some other metal and some other lanthanides also, as we will see as we go along. So next one, please. Yeah, this I already told, that analysis of stark components, that number of stark components, that the splitting of the emission spectrum due to the electronic field or ligand field is also can be correlated to the site symmetry of a particular metal ion. As I told you that for every J level, actually the maximum number of stark components that can be expected is 2J plus 1. And so 0-0 transitions, as I was telling you, that 0-0 transitions, only one component is expected. Okay, now 5D0 to 7F1, there are 3 components. 5D0 to 7F2, maximum 5 components are expected. So similarly, okay, see, if the number of stark components are less, then it's more symmetric. If the number of stark components are more, that means maximum you are observing, then the symmetry is very low. As we go from higher to lower symmetry, stark components increases, number of stark components increase. That will be explained next slide. Similar, as I told you, that's this. See, if you see, this is an octahedral field. This is octahedral, T2G to EG transition. Now, if because of Stark effect, I am going from octahedral to square pyramidal and then square planar. So I am going down the symmetry. So this is octahedral, this is higher symmetry. This is square planar, lower symmetry. This is square pyramidal, lower symmetry. So from higher symmetry, I am going to lower symmetry. What will be my effect? My effect basically is that instead of why it is happening, actually I am trying to explain why the number of star components increases. Now, when it has octahedral transition, you are seeing only one transition. You are seeing only one transition. But in case when you are going down the symmetry from octahedral to square pyramidal and square planar, you are seeing two transitions. You are seeing two transitions. Okay. So instead of getting only one peak here, you will get two peaks here. So that is why by lowering the symmetry, the number of star components of a particular peak increases. The peak basically splits. So more splitting, lower is the symmetry. No splitting, less is the splitting, higher is the symmetry. Okay, next one, please. Now, by looking at the number of star components, I can say what is the site symmetry of the species. Now, there are tables are available, like I have presented a table here. Directly by looking at the components of 7F2, 7F1 and 0, you can directly say what is the site symmetry, what is the point group, what is the group of the symmetry of the metal ion around which the metal ion is sitting. So from that, you can have a better idea that is it a lattice position, is it an interstitial position, is it a defect center, or what is it basically, that you can know. Next, please. Yeah, so this is a detailed of that table which I presented in the last slide. This is a detail from that table. As you can see, it goes from the least C1 triclinic to monoclinic, orthorhombic, tetragonal, trigonal, hexagonal, cubic. It goes again to this one. Okay, from lower to higher symmetry it is going. As you can see, the number of star components here is decreasing, isn't it? It's decreasing actually. So as the site symmetry is increasing, the number of star components are decreasing. That is what I was telling, that by just looking at the star components, one can predict what is the site symmetry in which my metal ion is situated, my metal ion is sitting, and from that you can have a better understanding what is the structure of the host. Next slide. What about other rare earth ions? Is it possible? As actually up to now, I was only discussing Europium 3+. Now, what about other rare earth ions? Is it possible for other rare earth ions also? Yes, it is quite possible. Like for dysprosium 3+, as we know, dysprosium 3+ is a blue-yellow transition. It gives blue and yellow transition in the visible region. It has also two transitions. One is the magnetic dipole transition, which one is blue, and one is yellow transition, which is electric dipole. As I told you, this electric dipole transition fellow, this one is forbidden. It's forbidden actually. So if you are seeing, as you can see, if we compare these two things, we can see that the magnetic dipole transition is less intense than the electric dipole transition. So by looking at the spectra, I can infer that this spectra has come from a dysprosium 3+ ion, which is situated in a less symmetric environment. Okay, less symmetric environment. Okay, next one, please. Samarium 3+. Samarium 3+, this is a typical emission spectra of samarium 3+. The first emission band at 560, this one, first emission band at 560 is a magnetic dipole transition. And the band at 645 nanometer, this one, is purely electric dipole transition, So if the electric dipole transition is higher in intensity, then I will get my metal ion is present in a low symmetry environment. Next one, please. Terbium 3+. Terbium 3+ has a very famous blue and green emission, and this blue emission is an ED transition, which is up to 7F6, and this green emission, which is from 5D4 to 7F5, is a magnetic dipole transition. Now in this case, in the particular case, if you see, the electric dipole transition is lower in intensity, whereas the magnetic dipole transition is higher in intensity. So this clearly suggests that this particular metal ion, this fellow terbium 3+, is present in a symmetric environment. That is why this electric dipole transition is lower in intensity. In fact, this particular metal ion is in an octahedral position, in an coordinated by 6 ligands. Next one, please. In case of gadolinium 3+, normally we ignore gadolinium 3+. It's a very humble metal ion actually. Gadolinium 3+, although it is not, the emission is not in the visible region, but it's in the near UV region. But it's a very, very important metal ion actually. It is one of the few metal ions which emit in the UVB region, ultraviolet B region. And if you see, there is a small band here, okay, which I have highlighted here, and which I have blown up here. Okay, there are actually two transitions. One is to 7F S7/2, and now this fellow at 307, this fellow at 307, this fellow as 307 is a magnetic dipole transition, and this fellow here at 310 is an electric dipole transition. Now, as you can see from this, that the electric dipole transition, actually the magnetic dipole transition is here is barely visible. So that means it's a highly asymmetric case. Then that is what I have taken. This gadolinium, this actually spectra, this spectra is actually gadolinium 3+ doped in borosilicate glasses. So that is why you can see that and in glasses, as we know, there is no symmetry. It's a very random thing. So that is why you are expecting, you are getting this type of spectra. Now, if it is a symmetric case, then the spectra will be entirely different. Next slide, please. Now we will go to some typical examples. Now let us take the example of Europium 3+ in SrZrO3. Now in SrZrO3, there are two sites. One is the Sr site, one is the zirconium site. Now Sr site is 8 coordinated, less symmetric. But in case of zirconium, as we can see, zirconium is represented by big green balls, strontium is represented by medium black balls. Okay, and the O oxygen is represented by small red balls. Now, if you put europium in this, europium, where it is going, you don't know. Is it going to strontium site? Is it going to zirconium site? Or is it going to an interstitial site? Now, when we did this, we saw that, first of all, zirconium, as I told you, zirconium is a 6 coordinated species here. Here's 6 coordinated species, the big green balls, and it's very symmetric because it's octahedral. And in case of strontium ions, which are medium black balls, they are cubic, they are less symmetric, so no center of inversion. So similarly, we saw that europium actually is going to 2 sites. It is distributing itself at both the sites, and as you can see here, europium in case of strontium site, the magnetic dipole transition here, is higher in intensity. But in case of zirconium, here the magnetic dipole, the electric dipole transition here, the electric dipole transition is higher in intensity. The electric dipole transition here in case of zirconium is lower in intensity. On the other hand, the magnetic dipole transition here is small intensity, and the magnetic dipole transition here is large in intensity. So from that, we can conclude that europium ion is distributing itself in 2 different ways. It is replacing both strontium and zirconium. So also, when it is in asymmetric environment, the electric dipole transition is very higher in intensity. You see, it is short-lived. It's short-lived. The lifetime is 1.4 milliseconds. But when it is present in symmetric environment, the lifetime is 6.1 milliseconds because it's a symmetric environment. Symmetric environments, not allowed. The transition is not allowed. It's forbidden. It takes time to come down. That is why. Now, next slide, please. Similarly, there is another species we can take, another matrix we can take, ZnP2O7, zinc pyrophosphate. In ZPO, there are two types of zinc environment. There is no other metal ion here. You may expect that, okay, zinc is there, only one metal ion is there. If I put europium, then it will go to only zinc side. No, there are two types of zinc. One is a 5-coordinated zinc, one is 6-coordinated zinc. Now, obviously, the 5-coordinated zinc is less symmetric. The 6-coordinated zinc is more symmetric. Okay, so here also we got different lifetimes and different transitions. You see, this is higher in intensity, this is lower in intensity. Okay, other way, this is lower in intensity, the magnetic dipole transition here is low in intensity, and here the magnetic dipole transition is higher in intensity. So that also suggests that you can probe the local structure by that. In fact, from the number of components, we deduced that the point group is actually C3V here, and the point group in case of 6 zinc is C6V. Now C6V is more symmetric than C3V. It's not perfectly octahedral, it's a distorted octahedral, but the symmetry is higher. Next one, please. Now take another example, strontium silicate. So strontium silicate, there are two types of strontium coordination. One is 9-coordinated strontium, one is 10-coordinated strontium, represented here. 9-coordinated strontium and 10-coordinated strontium. Now we have doped this thing with trivalent, not only europium, but dysprosium and samarium also. And we saw that while europium occupies both 9 and 10 coordination number polyhedras, samarium and dysprosium remain specifically in the 9 coordinated site only. So this type of information you cannot get in other techniques. Now why that was happening, that we investigated by using XAPS and theory. So we could explain why it is happening that only europium is occupying both the sites. Europium is occupying strontium 9 and strontium 10, but samarium and dysprosium are not occupying. They are occupying only the 9 coordination site. This we got it from we experimentally saw it, but theoretically we proved it by using ab initio theories. Okay, now next slide, please. Yeah, now I have come towards the conclusion. Now before I conclude, I would just like to highlight some divisional highlights, like we are the number of publications, and these are the two major instruments that we are having in our lab. One is the fluorescence lifetime spectrometer, all the results which we have, which I have present. This is the divisional facility, and these are national facilities. I welcome all the participants who are watching me, listening me, to use these facilities. These are national facilities, and it can be used with no cost actually. So this is the ESR spectrometer, that is electron spin resonance or electron paramagnetic resonance spectrometer, which we are having in our lab. And this is the photoluminescence spectrometer, which most of us are using. And this is a very robust and very powerful technique. As I told you, I have given only some of the highlights, some of the examples actually. So next one, please, last one. Yeah. So I thank all for your kind attention, and whatever I have discussed, I have just put in the form of energy level diagram. You can see all the energy level diagrams of the rare earths. Of course, neodymium 3+ and ytterbium 3+ comes in the near IR region. Their emissions are in the near IR region. Otherwise, all I have discussed. So thanks all. Thank you all for your kind attention, and I'll be happy if I'll be happy to answer if you have any questions. Yeah. So I can see the first question is from Malatesh Pujar. My query is, can we dope lanthanide to transition metals? If yes, elaborate it by considering cerium. I think you are. I think you want to ask can we dope lanthanides to transition metals? That means that means you have a transition metal oxide. In that you want to put lanthanide ion. Is it correct? I guess it is correct. But see, the main thing to notice here, that band gaps. The host should be a wide band gap material. It should not happen that the band gap of the material which you want to dope is more than the host itself. So if it is a transition metal ion, I don't know which transition metal ion you are referring to, but it is possible. It is possible, but not. I don't think it is for 3D. 3D. I think 4D you can do. Like tin oxide, people have done tin oxide. So it's possible, but only thing is that you have to take care of the band gap. If the host band gap should be wider than the dopant band gap. That is what I feel you want to ask. Okay, his second question is, how decide the element is allowed transition? Okay, this if I understand correctly, you want to ask that how to decide that the element is allowed transition. See, allowed transition is that, see, FF transitions are forbidden, I told you. FD transitions are allowed. So if delta L is equal to plus minus 1, then that is allowed transition. If delta L is equal to 0, then that's forbidden transition. Okay, that's what I think you want to ask. The second one is from Dhanalakshmi. Can we guess same type of site distribution for all ions other than europium? Yes, we can. Yes, we can. By looking at the star components, yes, we can guess the types of site distribution for other ions also. Yes. Next one is from Subhendu, Mr. Subhendu. Is there any limitation of Stark effect? Well, if it is a, I don't know, maybe it's not a, it's just a thumb rule. It's just a thumb rule. So there are limitations, but one should not take it as the technique, as the thing. You need to supplement it. You need to supplement it with something else. It will give you just an indication. Okay, this is the thing which we are tend to. It will just give you an understanding. Okay, it is not a definite thing. Of course, if it is a very symmetric thing, there are no Stark effects, there are no Stark components, then it is very difficult. So in case of lower the symmetry, better is the interpretation of Stark components. But higher symmetry cases, the interpretation of Stark components is rather difficult actually. I will put it that way. Okay, the next question is, in what state the samples will be accepted for SPL spectra measurements in your lab? In our lab, we do both solid and liquid. Powders are better. If it is a pellet, then also it's better. If it is a powder, then we can just smear it on the glass slide. And if it is a pellet, then also it's better. Liquids also we do, and that's it. We can do both.
Okay. One more question, sir.
Okay, one
more question is, can you please explain about the time-resolved spectroscopy?
Can we?
Time-resolved spectroscopy.
Time-resolved spectroscopy. Can I explain?
Explain.
Okay. See, basically, see, time-resolved spectroscopy, does it mean lifetime, recording the lifetime, or time-resolved emission spectroscopy? They are two different things actually. So he wants to know the lifetime, how to record the lifetime, or
no, spectroscopy, sir. Time-resolved spectroscopy. It is not the lifetime of the sample.
Okay, so See, time resolved spectroscopy, suppose I'll give you an example. I'll give you one specific example, time resolved spectroscopy. See, suppose I have a system, like I told you, that strontium case, or in all those cases which I have discussed, if you see that europium is present in two different sites, right? So, but when you do the emission spectroscopy, both type of europium emissions are buried in that. You are not going to see the two emissions. Suppose europium 3 plus is present at two different sites, but the spectrometer will show you only one spectra. It cannot identify, no. You need to separate the two species. How you can separate? That is actually the time resolved spectroscopy. What you have to do is, basically first you record, let us say there are two species A and B. Let us say there are two species A and B. A is a short-lived species. B is a longer species, long-lived species. You want to identify both the species. So what you have to do is, first you record A plus B. Whole spectra you record, full spectrum you record. Now what you do is, A plus B, as I told you, A is a short-lived species. What you do is, there is something called as time delay or time gap. What you do is, you allow the short-lived species to decay. I told you that lifetime of a particular species is 1/3 of the intensity becoming 1/3. 1/3. So if you allow 3 lifetimes, 1/3, 1/3, 1/3, so it completely decays. Okay. So suppose A is, first you record A plus B, you keep it. The spectra A plus B, you keep it. Now what you record is only B, the long-lived species, by applying a proper delay. Delay means how much delay you want to give. Let us say that depends on the lifetime of the short-lived species. If the short-lived species lifetime is, let us say, 1 millisecond. 1 millisecond is the lifetime of the short-lived species. So you give a delay of more than 3 milliseconds. Let us say 5 milliseconds. After 5 milliseconds, my short-lived species will not be there. You are getting my point?
Yes, sir.
So after 5 milliseconds, my short-lived species whose lifetime was 1 millisecond will not be there. I'll be getting only the long-lived species. I'll be getting the signature from only the long-lived species. That is B. Now I had A plus B. Now I have to minus B. Then I will get back A. So I told you, you first record the full spectrum, A plus B. Keep it. You give a time delay, sufficient time delay to record the long-lived species only. You will get B. Now you minus A plus B, minus B, you will get A. So now you have got B, you have got A. Now that is how I have explained it in a easier way, but it's not like that. You have to do some multiplications also when you are subtracting, but this is the way you can do it. This is the way it is done. It's not only 2 species. Actually, there are 3 species. The situation becomes complicated. 4 species, it is further complicated. So it's A plus B plus C. You first record A plus B plus C. You first subtract the shortest lived species. Then you record B plus C, then you record C. So it's a time-consuming job, but it's a very, very satisfying job, challenging job. In fact, when I first did this time-resolved emission spectroscopy, I was very happy. I could see the spectra. It's actually very, very happy moment when you see this different, the emission spectra. You can guess that, okay, this species is present in a symmetric environment. This species is present in a non-symmetric environment. It's a very, very happy thing, happy feeling. You cannot describe it. When you do it, you can feel it. So it's a very, very nice thing. Actually, you can do it. I think I explained. There is no other way I could explain it unless I go to a blackboard.
Okay, sir. Thank you so much.
Any other question?
Yes. They are asking for reference books. Right?
Reference books.
Books.
Reference books. I can remember one reference book is Blase. That is the best book, I think. Luminescence of solids, I think. Luminescence of solids or luminescence spectroscopy by Blase. You just see Blase. BLASSE. That is the best book I have read for beginners. That is one of the best books actually I have read. And to start with, actually, I think Rohatgi Mukherjee is the starting point. Fluorescence spectroscopy by Rohatgi Mukherjee, it's a starting point, and Banuel. Banuel is the starting book. One should read that first. Then you can go to any other book. But Banuel and Rohatgi Mukherjee, Banuel, Molecular Spectroscopy by Banuel. That is the first book one should read. And then you should go to other books. In so many books I am not getting. Only Blase I could remember.
Your books, sir, 3 books you have published, sir, on luminescence?
Those are not on luminescence. Those are on ESR and luminescence combined. And those are, one book chapter was on ESR, electronic spin resonance.
Okay.
One book was on material characterization.
Okay.
And one book was on characterization techniques of glasses. So that includes photoluminescent techniques also. But per se, photoluminescence I have not yet. On ESR, I have written. On ESR, electron spin resonance, I have written, but not on specifically on fluorescence.
Okay. Okay, thank you, sir. Thank you so much.
Okay, thank you, madam.
I think the participants are very happy to have such a session. The luminescence, when it is related to symmetry and the stark effect and all, it is a wonderful session, sir. Thank you so much for spending your time on this.
Yeah.
I thank the participants for your kind attention to sir's speech. You can contact sir for the further studies. Only 2 instruments were shown, but they are having a number of instruments. We know it's a national facility and sir is there. You can contact sir for the future. Thank you so much, sir. Thank you. Thank you to all the participants. We have given the feedback link. You can fill it for getting your certificates. Thank you, sir.